You know how some problems in math just feel like you've hit a brick wall? They seem completely impossible. But what's amazing is that sometimes all it takes is one new idea, like a single key, to unlock not just the answer, but a whole new world that you never even knew was there. And believe it or not, the key we're talking about today is hidden inside one simple, almost innocent-looking question.
So, check this out. It looks so simple, right? X squared plus 1 equals 0. Okay, let's just move the 1 over, and now we've got x squared equals negative 1. But, hang on, what number, when you multiply it by itself, gives you a negative 1? I mean, really think about it for a sec.
And that's the wall, right there. With all the numbers you and I learned about in school, the positive ones, the negative ones, fractions, the whole shebang, there's just no answer. It's a locked door. Period. And here's exactly why it's locked. Just think it through. A positive number times a positive number, that's positive. Okay, what about a negative times a negative? Well, that's also positive. So any real number you can possibly think of, when you square it, is going to end up positive or 0. So how on earth are we supposed to get to negative 1? So what did mathematicians do? They did something kind of brilliant and really bold. They just invented a key. They created a new number and called it I for imaginary. And they gave it just one simple, almost reality-bending rule. I squared equals negative 1. That's it. That's the whole deal. It's not something you prove, it's just a new rule for a whole new game we're about to play. And just like that, with that one little act of invention, the lock just breaks. This one new piece of the puzzle, it doesn't just solve our little equation. No way. It throws the doors wide open to this vast, hidden dimension of numbers. Okay, so what does this new world even look like? I mean, if these numbers aren't on that number line we all know and love, where are they? Well, it turns out they were hiding in plain sight the whole time. We just needed to add a new dimension. The answer was to add a whole second dimension. Welcome to the complex plane. That horizontal line, that's our old friend, the real number line. But now we've got this new vertical axis, and that's where all our new imaginary numbers live. So any number that has both a real part, A, and an imaginary part, B, we call that a complex number. And the cool thing is, you can plot it on this plane, just like you'd plot a point on a map. So if you want to find, say, the number 3 plus 4i, it's easy. You just go 3 steps over on the real axis, and then 4 steps up on the imaginary axis. And boom, there it is. All of a sudden, these abstract ideas aren't so abstract anymore. They're actual locations. All right, so we've got our map, but what are the rules? How do we navigate this new place? Let's take a look at how these numbers actually play together. Well, the good news is adding and subtracting is super intuitive. In fact, if you've ever done even basic algebra, you already know how to do this. You just combine the like terms. You add the real parts to the real parts and the imaginary parts to the imaginary parts. Seriously, it works exactly the same way. It's that simple. Multiplication is pretty much the same deal too. It's just like expanding brackets in algebra, but with one special little twist. There's only one new rule you gotta remember. Anytime you see an I times an I, that little pair simplifies down to negative 1. That's the secret sauce. Okay, now division. This is where things get really clever. To make division work, we need a special tool. It's called the complex conjugate. And yeah, it sounds kind of fancy, but I promise it's so simple. All you do is take your complex number and just flip the sign of the imaginary part. That's literally it. So the conjugate of, say, 3 plus 4i is just 3 minus 4i. So why is this little trick so incredibly useful? Well, here's the magic. When you multiply any complex number by its conjugate, the imaginary parts perfectly cancel each other out every single time. And you're always left with a plain old real number. And that is the secret to making division a piece of cake. So the whole trick for division is this. You want to get that I out of the denominator, out of the bottom of the fraction. To do that, you just multiply both the top and the bottom by the conjugate of the denominator. When you do that, the bottom instantly turns into a nice, clean, real number. And just like that, the problem becomes way easier to solve. It's this really elegant little hack for cleaning up the whole equation. Okay, so we've got the map, we've got the rules, but you might be asking, so what? What's the real point of all this? Well, this is where the magic happens. This is where we get to see the truly beautiful and totally surprising patterns that were hiding inside these numbers all along. Let's start with something we all know. What's the cube root of 27? Well, it's 3, right? Because 3 times 3 times 3 is 27.
Easy. But here's a question for you. Is that the only answer? In the world of real numbers, yeah. But in the complex world, the answer is a huge, surprising no. It actually turns out that there are not one, but three completely different numbers that, when you cube them, give you 27. One of them is our good old friend, the number 3, of course. But there are two others, and they've been lurking out there on the complex plane this whole time. And this is the truly incredible part. When you take those 3 roots and you plot them on our complex plane, they form a perfect, beautiful equilateral triangle. And that is not a coincidence. If you were to find the 4 fourth roots of a number, they'd form a perfect square. The 5 fifth roots, a perfect pentagon. It's like complex numbers reveal this hidden, beautiful geometric order that's woven into the very fabric of math. So what all this really shows us is that calling them imaginary numbers was kinda a historical accident. These numbers aren't fake or made up at all. They're a fundamental part of how the universe works. They're absolutely essential for everything from designing electrical circuits to understanding quantum mechanics. They don't just make our number system more complete, they give us a much more powerful and elegant way to describe reality itself. And that kind of brings us to a final thought. We started this whole journey with a problem that seemed impossible, right? And the solution was just daring to invent one new rule. It really makes you wonder, doesn't it? What problems that we face today, the ones that seem completely impossible, are just waiting for that one new elegant idea to come along and unlock a whole new dimension of what's possible.